ECG analysis algorithm. In this chapter, we will consider the sequence of the ECG analysis, so as not to miss any little thing and finally come to the correct diagnosis. Let's talk about the concept of the ECG recording speed. Let's talk about the determination of the heart rate, about the concept of the cardiac axis of the heart. Let's talk about the Einthoven's triangle and about the criteria for the analysis of the main elements of the ECG. Let's start talking about the ECG tape. Everyone saw the ECG tape, but maybe not everyone understands its meaning. Graph paper is applied on it. Each small square of this graph paper is 1 millimeter in height and 1 millimeter in width. A large square includes 5 small squares in height and 5 small squares in width, respectively. It is equal in height and width to 5 and 5 millimeters. From this, it is clear that 2 large squares are 10 millimeter wide. Every 3 squares are 15 millimeters wide, etc. Let's talk about the ECG recording parameters. Before analyzing the ECG, it is necessary to estimate and evaluate the parameters of the ECG recording, without which data analysis is impossible. These parameters are as follows. First, the recording speed. Second, the voltage and the leads. Now, let's talk about each of them. ECG recording speed. There are two most common ECG recording speeds. It's 25 millimeter in second and 50 millimeter in seconds. Remember, the higher the ECG recording speed is, then the more the waves and complexes, intervals and segments look more extended. It is not difficult at all to determine at what speed an ECG is recorded. Let's watch this video and you will right away notice what I mean. Look here how it slowly goes away, slowly, slowly, slowly. And look here how it's much faster. This is the difference between recording at the speed of 25 millimeter in seconds and 50 millimeter in seconds. The electrocardiograph automatically applies speed values to the tape. Usually, the speed is displayed at the bottom or at the top of the tape. Some devices do not apply speed values, but knowing the duration of the waves in normal and evaluating these waves on the ECG, you can understand how fast the ECG is recorded. To assess the duration of the wave, it is necessary to know the duration of the large and small cells at a certain speed. Let us stop on the ECG recording speed of 25 millimeters in seconds. This speed says that 25 millimeters of tape is recorded in 1 second, which corresponds to 5 large cells or 25 small cells. And if 5 large cells are recorded in 1 second, then 1 large cell is recorded in 1 second divided by 5. It is equal to 0.2 seconds. Accordingly, 1 small cell will be equal to 0.2 seconds divided by 5. It will be equal to 0.04 seconds. Let's summarize. At an ECG speed of 25 millimeter in seconds, the duration of 1 small cell is 0.04 seconds, and the duration of 1 large cell is 0.2 seconds. Let's consider an example. A P wave is recorded on a tape of a speed of 25 millimeter in seconds. We define its boundaries and calculate how many cells it makes up. In this case, it's about 2.5 small cells. Let us calculate its duration. We multiply 2.5 cells by the duration of one small cell. It is 0.004 seconds at the speed of 25 millimeters in seconds. Therefore, the duration of the P wave in this case is 0.04 is multiplied by 2.5. This is equal to 0.1 seconds, which corresponds to the normal duration of the P wave. You can also calculate it another way. 2.5 cells, this is a half of a large cell. Accordingly, you can divide the duration of a large cell by 2. In the speed of 25 millimeters in seconds, the duration of a large cell, like we said, is 0.2 seconds. This means that 0.2 seconds is divided by 2. It is equal to 0.1 second. Then the duration of the P wave is 0.1 second. Similarly, consider an ECG recording speed of 50 millimeters in seconds. This speed means that 50 millimeters of tape is recorded in 1 second, which corresponds to 10 large cells. This means that 10 large cells are recorded in 1 second. This means that 1 large cell is recorded in 1 second divided by 10 cells. It is equal to 0.1 second. This means that the duration of 1 large cell is equal to 0.1 seconds. Accordingly, the duration of a small cell is equal to the duration of a large cell divided by the number of small cells in it. This means 5 pieces. Accordingly, 0.1 second is divided by 5. It is equal to 0.02 seconds. This means that at an ECG recording speed of 50 millimeters in seconds, the duration of one small cell is equal to 0.02 seconds, and the duration of one large cell is equal to 0.1 seconds. Let's consider an example. A P wave is recorded on a tape at a speed of 50 millimeters in seconds. We define its boundaries and calculate how many cells it makes up. In this case, 5 small cells. Let's calculate its duration. 5 cells are multiplied by the duration of one small cell. At the speed of 50 millimeters in seconds, the duration of one small cell is 0.02 seconds. Therefore, the duration of the wave in this case is 0.02 seconds multiplied by 5. It is equal to 0.1 seconds, which corresponds to the normal duration of the P wave. Let's now talk about the ECG voltage. ECG voltage can be determined by 2 places on the tape. First place, second place. First place is the bottom or can be on the top of the ECG tape, depending on the model of the electrocardiograph. The figure shows the voltage of 10 millimeters in millivolts. This is the standard voltage of the ECG. The second place is the rectangle-shaped wave, which is located at the very beginning of the ECG recording. What does this rectangle-shaped wave means? The height of this wave is the voltage of the ECG. In this case, the value of this wave is 10 millimeters in millivolts. Respectively, the voltage of the ECG is 10 millimeters in millivolts. Attention! If 10 millimeters in millivolts is written below or above the ECG and the height of the wave will not be 10 millimeters, this means that the electrocardiograph is not calibrated and it is impossible to analyze the ECG. Let us now talk about the ECG leads. As noted in the first chapter, in order to record an ECG, it is necessary to apply electrodes on the human body. Each electrode records a potential. The potential difference between the electrodes is called leads. The limb leads and the chest leads. The limb leads are divided into 2 parts. The standard leads or in other words, bipolar leads, the first, second, and third leads, and the unipolar leads, or the reinforced leads from the limbs. It is AVR, AVL, and AVF leads. The chest leads are V1, V2, V3, V4, V5, and V6. Let us talk about the standard leads. First lead. It records the potential difference from the right arm and the left arm. The second lead records the potential difference from the right arm and left leg. Third lead records the potential difference from the left arm and left leg. Why are they bipolar? Because the two sides of the electrodes have a potential. Now let's talk about the unipolar leads. The unipolar leads differ from the bipolar leads in that on the one hand the potential is taken from the limb, and on the other hand the potential should be zero. This zero is achieved by combining two electrodes from other limbs through resistance. It is called the combined Goldberg electrode. Because of that, they are called unipolar, because one of them is equal to zero. But in the bipolar ones, the both sides have a potential. The unipolar leads are recorded in the following way. AVR, it is enhanced lead from the right hand. AVL, it is an enhanced lead from the left hand. AVF, it is an enhanced lead from the left leg. AVR, letter R because it's right, AVL, letter L because it's left, and AVF, letter F because it's foot. Now, let's talk about the chest leads. Chest leads are formed exactly in the same way as the unipolar leads. In other words, this means that on one side, the electrode records the potential from the electrode mounted on the chest, and on the another side, the combined potential is equal to zero. This zero potential is achieved by combining three electrodes on the extremities, the right arm, the left arm, and the left leg. Let's go back to the standard leads. They can still be represented in the form of a triangle placed on the human body. This triangle was proposed by William Einthoven. He is a Dutch physiologist, the founder of the electrocardiography. According to Einthoven's theory, a point is located in the center of the triangle. This point is the heart. Each of the leads can be superimposed as a parallel axis. It means a straight line passing through the heart. First, second, and third. Next, we draw the axis of the unipolar leads from the center to the limbs, AVR, AVL, and AVF. Now it's easy to figure out which lead is responsible for which part of the heart. From the figure, it follows that leads AVL first and second, they shoot the left side of the heart. Leads AVF and the third, they shoot the bottom of the heart. AVR lead shoot the right atrium. Let us more specially consider which lead is responsible for which part of the heart. Lead 1 is responsible for the front wall of the heart. Lead 3 is responsible for the back wall of the heart. Lead 2 is the sum of the first lead and the third lead. AVR, it is responsible for the right side wall of the heart. AVL, it is responsible for the left anterolateral wall of the heart, or in other words, the left frontal side of the heart. AVF, it is responsible for the back lower wall of the heart. Now, let's see what the chest leads are responsible for. The figure shows the recording electrodes located on the chest. This figure shows that the leads V1 and V2 are responsible for the right heart, for the right ventricle. V3 is responsible for the interventricular septum. V4 is responsible for the apex of the heart. V5 is responsible for the anterolateral wall of the left ventricle. V6 is responsible for the lateral wall of the left ventricle. Remember, the cardiac axis is directed to the fourth lead, to the V4 lead. Because of that, in V4, the R wave will be the highest. Now we can easily summarize. First lead, AVL, V5 and V6 are responsible for the left side of the heart. Third lead, AVF, V1 and V2 are responsible for the right side of the heart. Always remember this triangle and you will guess everything fastly. Now, let's talk about the ECG analysis sequence. After determining the parameters of the ECG recording, so then we can interpret and analyze the electrocardiogram in the following order. First, we should analyze the rhythm. This means first, rhythm analysis, regularity and pacemaker. Second, heart rate. After that, the cardiac axis. After that, analyze of the waves, complexes and segments. We all this analyze by order. First of all P, after that QRS, after that ST, after that T wave. And then we analyze the remaining intervals and segments, PQ, QT, etc. Any ECG must be evaluated in this order. First of all, let's talk about the rhythm analysis, regularity and pacemaker. The rhythm is considered correct if all RR intervals are the same. A discrepancy of plus and minus 10% is allowed. The distance RR can be determined visually or using an ordinary ruler. Look how all RR intervals are equal to 2.1 centimeters. But when the intervals RR are different, this means more than plus minus 10%, then the rhythm is incorrect and it's called arrhythmic. Let's take an example. Look here, 1.4, 1.1, 2.3. It means that the rhythm is arrhythmic. Now, let's talk about the pacemaker. Always remember, normally the pacemaker should be the sinus node. This means that the excitation always should start from the sinus node. We talked about that in the first chapter, in the video of the conduction system of the heart. You can go back and watch this video. In order to determine if the rhythm is sinus rhythm or not, then there are certain criteria. First, depolarization begins at the sinus node. This means that P wave must be positive in the second lead and must be negative in the AVR lead. It must be remembered that. The P wave can be positive in the first lead and in AVF lead. In leads V1, V2, P wave can be positive or two-phase. When we see all of that, this means that the depolarization begins at the sinus node. Secondly, P wave must precede the QRS complex. P wave must be before every QRS complex. Third, the shape of the P wave should be constant, permanent. This means that the shape of the P wave should be the same in all leads. Generally, P wave can be in the following shapes. It can be positive, negative, no P because it is on the R wave and it is not visible. After QRS complex, each one have its own pacemaker, but only this means that the pacemaker is the sinus node. We will talk about each one in the next chapters. Now let's talk about the heart rate. Heart rate is equal to 60 divided by RR in millimeters times T, where 60 is 60 seconds. RR is the distance in millimeters between two waves, between two R waves. T is the duration of a small cell of the ECG tape. At a speed of 25 millimeters in second, T is equal to 0.04 seconds. At a speed of 50 millimeters in seconds, T is equal to 0.02 seconds. Normally, the heart rate is from 60 to 90 beats per minute. Let's take an example. Example 1. We determine the heart rate on an ECG tape recorded at a speed of 25 millimeters per second. Measure with a ruler the RR intervals. In this case, it is equal to 20 millimeters. T is equal to 0.04 because the tape is recorded at a speed of 25 millimeters in seconds. We substitute these data into the formula and calculate the heart rate. Heart rate is equal to 60 divided by RR times T. Heart rate is equal to 60 divided by 20 times 0.04 seconds. It is equal to 60 times 0.8. It is equal to 75. In this case, the heart rate is 75 per minute. Example 2. We determine the heart rate on an ECG tape recorded at a speed of 50 millimeters in seconds. Let's measure with a ruler the RR intervals. In this case, it is equal to 32 millimeters. T is equal to 0.02 because the tape is recorded at a speed of 50 millimeters in seconds. We substitute this data into the formula and calculate heart rate. Heart rate is equal to 60 divided by RR times T. It is equal to 60 divided by 32 times 0.02. 60 divided by 0.64. It is equal to 94. In this case, the heart rate is 94 per minute. Now, let's talk about the electrical axis of the heart, or in other words, it is known as the cardiac axis. The cardiac axis is the total vector of the electromotive force. In other words, it is the general direction in which the heart depolarizes. Notice, the definition is wonderful, but not clear to everyone. Let's see what is the cardiac axis. Excitation comes from the SA side and spreads throughout the heart. In the figure, we presented it conditionally with blue arrows. They are excitation vectors on each part of the cardiac conduction system. If all these vectors are summed, then we get one big vector, which will be directed in one certain direction. This will be the electrical axis of the heart. Let us analyze pathologies that lead to a deviation of the electrical axis of the heart. There are many of them. These are block of the legs of the bundle of hairs, the hypertrophy of various parts of the heart, and myocardial infarction, etc. For example, the figure shows that with hypertrophy of the left ventricle, its wall is thick. Therefore, we see the excitation vectors were spread more to the left side of the heart due to the large mass of the left ventricular myocardium. And if in this case we summarize all these vectors, then the cardiac vector will be rejected to the left. The same rule is applied on the right axis deviation. We can see that if we summarize all these vectors, then the cardiac vector will be rejected to the right. Deviation can occur in both cases, normally and with various heart diseases. Normally, for example, in obese people, due to the high elevated diaphragm, the heart is located more horizontally. Respectively, the cardiac axis can deviate to the left. And on the other side, In thin people, the heart and the cardiac axis can be located more vertically. Let us return to the Einthoven triangle, on which all the leads are drawn. This triangle can be supplemented by drawing a circle around the leads. We divide the circle into a dial with degrees from 0 to plus 180 and from 0 to minus 180. The electrical axis of the heart can be represented as a vector coming from the center of the circle at a certain angle called the angle alpha. If the angle of the cardiac vector falls in the range from plus 30 to plus 69, then this means that the electrical axis of the heart is normal. If this angle falls in the range from plus 0 to plus 30, then this is an horizontal deviation. If the angle falls in the range from plus 0 to minus 90, then this is a deviation of the electrical axis of the heart to the left. In other words, it is a left axis deviation. If this angle falls in the range from plus 70 to plus 90, then this is a vertical electric axis of the heart. If this angle falls in the range from plus 91 to plus 180, then this is a deviation of the electrical axis of the heart to the right, or in other words, it is a right axis deviation. Let's summarize. Normal cardiac axis is when angle alpha is from plus 30 to plus 69. Horizontal cardiac axis is when angle alpha is from 0 to plus 30. Left axis deviation is when the angle alpha is from 0 to minus 90. Vertical cardiac axis is when angle alpha is from plus 70 to plus 90. The right axis deviation is when the angle alpha is from plus 91 to plus 180. Let's talk about how to determine the electrical axis of the heart on the ECG. The size of the Q, R, and S waves in standard leads largely depends on the location of the cardiac axis. In order to understand how cardiac axis affects their value, we return to the Einthoven triangle. Let's place the vector of the normal electric axis of the heart in the center of the triangle. Next, drop the perpendiculars to each lead. This is the black dashed lines in the figure, and project the cardiac vector on them. You can notice that the length of the projection on the leads turned out to be different. Then we placed the QRS complex in their projections. The figure shows that in lead 2, the QRS complex is the largest. In the first lead, the QRS complex is slightly smaller, and in the third lead, the QRS complex is the smallest. From here, we can form a rule. For the normal cardiac axis, the R wave in the second lead is higher than the R wave in the first lead, and the R wave in the first lead is higher than the R wave in the third lead. In any case like this, we can say that the cardiac axis is normal. On an ECG, it looks like this. The R wave in the second lead is higher than the R wave in the first lead, and the R wave in the first lead is higher than the R wave in the third lead. Now, let's consider the left axis deviation. Again, let's lower the perpendiculars to each lead and project cardiac vector on them, and then place the QRS complex in these projections. In this case, the R wave is the highest in the first lead, in second lead a little less, and in the third lead is the smallest. From here we can form a rule. The electrical axis of the heart is deflected to the left if the R wave in the first lead is higher than the R wave in the second lead, and the R wave in the second lead is higher than the R wave in the third lead. Now, let's consider the right axis deviation. We again project the cardiac vector on the leads and place the QRS complex in these projections. We see that the R wave is the highest in the third lead, in the second lead a little less, and in the first lead it is the smallest. From here we can form a rule. The electrical axis of the heart is deflected to the right if the R wave in the third lead is higher from the R wave in the second lead, and the R wave in the second lead is higher from the R wave in the first lead. Now let's summarize. Normal cardiac axis is when R2 is bigger than R1 and R1 is bigger than R3. Left axis deviation is when R1 is bigger than R2 and R2 is bigger than R3. Right cardiac deviation is when the R3 is bigger from the R2 and the R2 is bigger from the R1. We can note that it's not always possible to determine the cardiac axis on the ECG by the size of the R wave in the leads. It happens that the R wave are approximately the same in all leads, and it is so difficult to determine where it is higher and where it is lower. Because of that, in such a case, for a more accurate determination of the cardiac axis, the angle alpha is calculated. To determine the angle alpha, it is necessary to take the QRS complex in the first and the third lead and add up the size of the Q, R, and S waves for each lead. Now we'll take an example. When calculating, it must be taken into account that if the wave looks down from the counter, then its value will be minus sign. And if the wave looks up from the counter, then its value will be a plus sign. Look how Q plus R plus S minus 2 plus 6 plus minus 3, it is equal to plus 1. And here the same way. As a result, we get two results. The sum of the wave of the first lead is equal to plus 1, and the sum of the waves of the third lead is equal to minus 3. We substitute the obtained values into a special table for determining the position of the electrical axis of the heart, plus 1 and minus 3. The line drawn from the center of the table through the intersection of the projections of the two values, which we determined above for the first and third leads, will indicate the value of the angle alpha. In this case, it is minus 70. Remember, we said that if the angle alpha is in the range from plus 0 to minus 90, and this it is minus 70, it means that it is in this range. Then this is a deviation of the electrical axis of the heart to the left. In other words, it is a left axis deviation. Now let's move to the simplest, or in other words, it is called the everyday way of determining the cardiac axis. In the figure below, we see three fragments of an ECG. On the ECG tape, we place an ordinary pencil as follows. The non-pointed side of the pencil is applied in the corner of the ECG tape, and its continuation is superimposed on the R wave in the lead in which it is the highest. You can clearly see how the cardiac axis is located. On the first fragment, the pencil connects the corner of the tape and the R wave in the second lead. This is a normal cardiac axis. On the second figure, the pencil connects the corner of the tape and the R wave in the first lead and lies more horizontally. The cardiac axis is deflected to the left. By the same principle, we place the pencil on the third fragment. It is seen that the cardiac axis is deflected to the right. If in this way it is impossible to determine the direction of the cardiac axis because it's not visible or not clear, for example, then we return to the calculation of the angle alpha. Now let's talk about the analysis of the P wave. When looking at the P wave, we should determine its shape. It should be always similar. It should be always positive in the second lead and always negative in the AVR lead. In other leads, it's often positive or two-phasic. We should determine its duration. Normally, it is up to 0.1 seconds. We should determine its height. Normally, it's up to 2.5 millimeters. Analysis of the QRS complex. When we look at the QRS complex, we should determine whether the QRS complex is similar or not. Normally, they are always similar. We should determine its duration. Normally, it is up to 0.1 second. We should determine the height of each wave. For that, pay attention to the following figure. It shows how the height of the R wave in different chest leads changes. Normally, the R wave increases from V1 to V4. It is called the progression of the R wave. In V4, the R wave is of maximum height, and further from V4 to V6, it gradually decreases. Normal height of the Q wave is 1/F4 of the R wave. This means that, for example, if the R wave is 4 centimeters, then Q wave should not be more than 1 centimeters. ST segment analysis. When considering the ST segment, we pay attention to its location relative to the counter. If the ST segment lies on the counter, or above the counter, or below it. Normally, the ST segment should be on the ISO line, but depression, in other words, below the ISO line, in leads V5 and V6 is allowed up to 0.5 millimeters, and a rise, elevation, in leads V1 and V2 is allowed up to 2 millimeters. No, in such a case, the T wave should be positive. Other changes in the ST segment will be considered as a possible pathology of the heart. Analysis of the T wave. Analysis of the T wave includes determining its shape and height. Normally, T wave is negative in the AVR lead, positive in the first, second, AVF, V2, V3, V4, V5, V6 leads, and in the third, V1 and AVL leads, it can be positive, negative, or biphasic. Analysis of the PQ and QT intervals. When considering these intervals, we should pay attention to their duration. Normally, PQ interval is up to 0.2 seconds. QT interval is up to 0.44 seconds.